right, first, thank you for having me. So as you said, like we met at Napoli, but I've been following like Software Mention like for a while online. First, I thought like we were the only one at Telnyx doing Elixir and WebRTC, but we found out that other folks do that, which is great. I'm just afraid like we are the only one, and we are all in this room. But thanks to conferences like that, probably that will change in the future. So some words about me. I'm a software engineer at Telnyx. Telnyx is a communication as a service platform where we can handle phone calls and messaging and these kind of things. And in my squads, especially, I'm working with phone calls. And yeah, so I build APIs using Elixir to interact with live phone calls. And also, like, as you can see, I'm training for marathon. So if you want to speak about marathon, I'm also happy to talk about that. All right. So this year, I mean, around 2033, I mean, last year, more or less, the team decided to provide the LLM power to our user using phone calls. And we decided to find a way to integrate that to their call flow. And today I will go through our journey to do all of that. It wasn't easy, to be honest, but we managed to get to something more or less good. And there are still some improvement that can be done, especially like you might have seen that during the talk from Rob yesterday, that there are new models that are coming up. So it's a domain where it keeps changing every day. So first, let's jump into the first iteration we decided to make. Something very simple, like we decided to do, as most people do for this kind of application, to divide it into speech to text. So we transcribe the audio from the user, we send that to the LLM, and then we generate audio out of the text from the LLM. So let's see how we get there. So at Telnyx, we already have like some features that allows our customer to do that. Like you can enable transcription on the call. You can also like, we also have like a open AI-like endpoint for chat completion. And we also have like a command that you can use to send text, I mean, to have any text being sent into the call and being played as audio. So our basic idea was, okay, let's build an application. Here you can see like for the Elixir folks out there, we decided to use Elixir. That just receives like a webhook every time there is a transcription, then send a request to the LLM, we wait for the response, and then we send a speak text. Of course, you guys might already see what problems are coming with that. So first one is super slow. So because of our system, it's super slow, but we will see how we are going to fix that later. Yeah, so for the latency, usually like in a normal conversation between humans, like you expect like 300 milliseconds to 1 second to get an answer. Otherwise, it's way too slow. So we want to have the same kind of thing for a voice assistant. And here you will see like I will use a lot the terms like time to first audio. I don't know if it's the right term, but it's the time it takes for the user to get the first audio after he stopped speaking. So in our first iteration, we managed to get to something between 6 and 10 seconds. It's not acceptable, like no one can use that. And the second issue we faced was the user experience. Like it was very hard to handle like interruption with our system. Like if the bot start to talk, like you cannot interrupt it. I mean, not fast enough. Or if the human is making pause when they are speaking, the bot might think like, oh, it's my turn, and that creates issue. So in the next slide, I'm going to focus on the latency first. So how we brought down that latency to what we have today. Okay. So one thing we didn't use at the beginning, which was a bit stupid, but it was first iteration, is to use the LLM streaming capabilities. as you may know, like the LLM can output tokens, token after tokens. And at the moment, we were waiting for the full response for the LLM, which can be super long. It depends on the response. So the LLM response time depends of the time to first token. This is very important. The tokens per second it can output, and the amount of token that are part of the response. And what we wanted to remove from the equation is the total count of tokens that are being generated by the response. Because if you think about it, like the LLM can stream tokens, and as soon as we get enough token, we can build an audio and send it back to the user. So that was our goal. So the way we've done that was to buffer the tokens from the LLM until there is some kind of punctuation, and then send that to the text-to-speech generation and send that to the user. It's not perfect, but with this, we managed to get to 3 to 4 seconds for the time to first audio, which is a bit better, but it's not perfect yet. Then, in the previous slide, I was showing you something that could be built by our customer because it's features that we already have, right? So instead, we were like, okay, we own the full stack, so let's get closer to the media. And that's where Membrane came out of it. So at Telnyx, we use Elixir a lot. And Membrane was offering us the possibility to directly receive media into our Elixir service using RTMP, which was great for our use case. Our media server supports that, so we decided to get to that. So this is a very simplified view of how it looks like. You can see like the voice assistant received the media from the Telnyx media server, and it's responsible to build like the voice assistant media back to the Telnyx media server, and we send that to the user. With this new method, the problem is like now we have to deal ourselves with detecting end of speech out of the media to cut the audio, etc., trigger the transcription out of the audio we've been cutting, and trigger the response generation and all of that. So we have some stuff to build now. Okay, so to detect end of speech, the very first thing we decided to do was a very naive approach where we decided to say, okay, if there is 800 milliseconds of silence in the audio I'm receiving, that might be an end of speech from the user. And as you can see, like we didn't want to wait until the 800 milliseconds are passed to actually trigger the answer generation. So we also decided to buffer like 100 milliseconds of audio at the beginning. We always buffer 100 milliseconds of audio, and if it's full of silence, then we trigger the answer generation, and the end of speech window will only confirm this, and that way we have like around 700 milliseconds to do as much computing as possible within this end of speech detection window. And here, when I'm talking about silence detection extra, we are doing something very naive where we just calculate the power of the audio and we apply some threshold. So it's not compute intensive, but it's very naive, right? If you are in a noisy environment or stuff like that, not ideal. But we will see that later. And so for the Elixir and Membrane folks out there, this is a bit how it looks like with a simplified view. We have a Membrane pipeline that receives the RTMP stream. Then we have one of the Membrane filter that is responsible for buffering the audio until like a silence. And we have like some processes that handle like the whole conversation. And this process will trigger another process for each answer generation. And this was largely inspired by, I'm sorry if I pronounce it wrong, Lars Wickman, who did a live transcription example with Membrane, and we largely inspired from that. So with all these changes, we managed to get around 2,500, between 2 and 3 seconds for time to first audio, which is not that bad, but still not good. And here I've made like a latency breakdown so you can see what's left in this 2 seconds to 3 seconds. Of course, all these numbers are dependent of our hardware and our software, whatever we use. Oh, and actually, I forgot to mention one thing. The goal of this project was to try to use open source models. So we use Whisper for transcription. We use Llama 3.1 70 billion for the LLM. And we use Style 2 TTS for the speech generation, but I will come back to that later. And I know like there are very good products out there like 11 Labs or OpenAI that do very great things, but we wanted to have something open source that we could use. Okay. So to reduce the latency of the transcription, the very first idea that came up was to use distilled Whisper, which is a distilled version of the Whisper model. It claims to be like 6 times faster. In our experiment, like we managed to get down to 250 milliseconds. And the quality was still good enough for our use case, so we were happy about that. So we will keep that for the first round of iteration. Now, we have a squad dedicated to that in our company that runs LLM on GPU and provides us API to run them. So I know like they've been doing some work like changing some hardware and changing like the software that they use to scale the LLM and distribute them. And with that, we managed to run Llama 3.1 70 billion to 50 milliseconds time to first token and around 40 tokens per second, which is pretty good because what you have to think also is like in average, you need around 10 tokens to get the first audio chunk that you can send for people. All right, so the next piece was improving the text-to-speech API. This came out not only for latency, but we found out this product from 11 Labs that has a very great API to interact with text-to-speech that fits very well with large language model. They have a WebSocket API where you can send like a token per token, and then they do some kind of buffering on their side, and then they return audio chunk as they are ready, which is pretty cool for us to use. And we decided to build something similar. The buffering is done on our side, so it's not as perfect as them. And it was very convenient for our other service to use, so we decided to build something like that, and we decided to use Style 2 TTS to build that. And with that, we managed to get to something around 500 milliseconds to generate audio out of the token that it receives. So from the first token we send to the first audio chunk we get back, around 500 milliseconds. Now, the next part was, so that was for latency. As you can see, like we get to something around 900 milliseconds to 1 second, we start to be good. So we decided to focus then on the user experience. The user experience. So first thing we decided to do was to modify this end of speech detection that we had because it was based on silence and we couldn't get down. I mean, imagine like the whole pipeline gets better. We will never manage to get down to these 800 milliseconds of silence before we can actually output something. And also, we wanted to have a way to detect pause and things like that in human speech, because between human, we should be able to understand like when someone is done speaking. So we were like, okay, maybe we can find a way to train a model that would be responsible for only that. So we trained a model that classify audio as end of speech or not end of speech. And we managed to run it with like 10 milliseconds inference. And if you are curious, like there is way more detail on Hugging Face on how it's been built extra. It's not myself, it's one of my colleagues, Stefan Petrovsky, who is not here today, that deserves all the credit. But if you are curious, you can check. One thing about this model, it wasn't perfect, of course, right? However, I feel like, we found out that if we embrace like the handling of the false negative and false positive of the model, we can still use it. So the false negative of an end of speech model here, it's like it doesn't detect end of speech when it should have. So for that, we can keep like the 800 milliseconds audio to trigger the end of speech anyway. This increased the latency by 800 milliseconds when this happened. And the false positive of the end of speech model are, it detects end of speech when I'm actually not done talking, for example. And in this case, what we do, it's like, because the processing still take a bit of time, if the user speak again, then we will stop the audio generation and get back to buffering audio, etc. So it's been working more or less okay to have these two. And what we found very cool, it's like when we handle both this problem, we can improve our data set to keep training our model with this false negative and false positive example to get it better. I'm not sure like if at some point we get to something that is very perfect, but so far it helped us. Okay, and there is something I didn't told you. So right now, I mean, I told you that at the beginning, we are always calculating the power of the audio, etc. So if you are in a noisy environment, it's a pain. Like, for example, if I'm on the phone with the voice assistant and there is some noise, it might think I want to interrupt it, and that's problematic. So we decided to start using a zero voice activity detection model, which has been working very good for us. And also what's interesting about this model, it has an API where you can pass, I mean, every time you pass a chunk of audio, it will also give you back like some kind of state matrix that you can keep passing back, and it will keep track of the voice of the caller. And this allows us to deploy the voice activity this voice activity detection model in a distributed way, and it was pretty cool. And also inference is pretty fast, so it was working great in our use case. Also, what is going to happen next, probably, we didn't do fully that yet, but we are going to probably apply full noise suppression into the stream that we are getting. That way we can reduce this kind of occurrence. Okay, so I managed to do the demo, so that's great. So here I'm going to show you a demo. I hope the audio will be okay, of me talking with the bot. I did that recently. Let me try to get... oh, okay. All right. I hope the sound is not too loud, so be careful. Does it say play? No. All right.
Hello, I am the RTC.ON demo assistant. How can I help you today?
Hey, can you tell me what is WebRTC?
I think you meant WebRTC. WebRTC stands for Web Real-Time Communication. It's a set of API and protocols that allow for real-time communication.
Wait, and what is the RTC.ON conference?
RTC.ON is a developer conference that focuses on sharing expertise in WebRTC, streaming, and AI development areas. It's a place where developers and experts come together to share knowledge, learn from each other, and showcase the latest advancements in these fields.
Okay, thank you.
If you have any more questions about WebRTC or the RTC.ON conference, feel free to ask.
Well, what is the capital of France?
That's a bit off topic, but I'd be happy to help. The capital of France is Paris.
All right, yeah. So
Great, thank you.
So yeah, I always ask, I mean, that's kind of a joke because I always ask when I work with the voice assistant, what is the capital of France? Because when you work with this, like unless you have an automated way of working with this, you never know what to tell to the assistant. So I always ask what the capital of France, and at least I know the response. So I can be sure like it doesn't try to fool me. And yeah, on a side topic, one day we were working on this text-to-speech generation, and I got super scared because like the text generation didn't work great, and at the end of the response, like there was a sound that was horrible, that made me scream. Like it was. I won't make it listen to you here because it would be bad. But if you are curious after, I can show it to you. All right. And so yeah, so this is just a last slide that summarize a bit everything. of course, here there are a lot of opinionated choices like using Membrane and Elixir, but we use that because in our company we use it a lot and it's fun to work with. And so far it's been doing great for us. What's important is the latency for any voice assistant. Like if it's too big, no one will use this product. And yeah, one thing like that didn't, I mean, this project took a while, and iteration was one of the most important things, like build something, measure, build, measure, and so on. And yeah, that's it. Thank you very much for your attention.
Questions time. Boris. In the back, over there.
Thank you. That's super impressive, and I'm gonna forward this to my colleagues because we're dealing with the exact same problems. It looks like a big chunk of the latency comes from the generation of audio. Have you considered prepending some pre-generated responses to get rid of that?
So that's an excellent question. We try to do that, like like in the representation of yesterday, like sending okay or great, and then first we had like a bunch of one like great, etc., and we were picking them randomly. And if you say something like, "Hey, my cat died," and then great, like we wanted to avoid that, but that's something we try at the beginning for sure.
What about comfort noise? Maybe something like that?
Yeah, that's something we will do next. First, to have comfort noise during the whole call, because I mean, when you're on the phone, there is always some noise, and here you are talking to the machine and there is no noise going out. So that would be one of the things we will do next. Probably in 1 month we will have it. So yeah.
Thank you.
I guess father of membrane.
The membrane was not my idea originally, so I don't think that's accurate.
Come on.
However,
You adopted it.
Yeah, I adopted it kind of. Yeah, excellent presentation. I'd like to ask if you're using calling the AI models from the separate services always, or you do that from Elixir directly as well?
So that's a very good question. So we separated the services, but for example, for transcription, we use NX, and we use, we run like the distilled whisper model on NX. For the rest of them, I think the LLM uses Python, but they are all different services. We had some trouble at some point where we wanted to also run some ONNX model on Elixir, because we use AMD GPU, and it became a bit difficult to use ONNX model with RTX library, etc. But we try a bit of everything, and yeah, but most of the time it's a different service that will handle that, either Python or Elixir.
Okay, and the speech-to-text is done then via Bumblebee or directly via Onyx or via something else?
For the speech-to-text, we use Bumblebee.
Okay, great, thanks.
Any further questions? Piotr, in the front.
Few, actually. The first one is about, if I understand correctly, you have the strategy of like, hey, I have the first stage that thinks that the user stopped talking, and then I confirm that the user actually stopped talking. And every time that you have this like false positive, you actually trigger llama response. Does that happen a lot? Do you get a lot of like usage of LLM caused by accidental calls that never succeeded?
We still have some of it, yeah.
Is it a substantial amount, or is it?
No, it's more like I would say from experience around 60%. So the accuracy of the model is not yet very good, but yeah.
Okay, and another one is about kind of a little bit to those like automated prepending of responses. I also noticed that, OpenAI has the same strategy, I believe, of prepending the answer with something like okay, but they also have this problem of the model always want to finish the conversation. And I also noticed that in your demo, you said, okay, thank you. And I was like, oh, if you have anymore, is that always happening, that the model is always the last to finish the conversation?
That's a good question. So In our product, here, for example, like you can define what we call an assistant, and like what 11 apps call an assistant, and it's plugged to the call and it talks forever. Like if you keep talking. However, we felt like that might not be like the best product to offer to our customers, so we try to narrow the scope. And for example, we offer an API where people can just say like, try to gather me like the name and the location of the caller, for example. And when the LLM is done doing that, it will trigger like a function call and we will stop everything.
Okay. Okay, cool. And the last one is, you also showed that in the demo, but was not really explained in the presentation, interruptions.
Ah, that's a good point.
Like, how is that happening internally?
So right now, like we detect, so we can detect like if there is voice activity or not. And we receive like this packet, and as soon as we have like a packet that detects voice activity, we stop anything that we are playing. And we kind of buffer like what has been already played to the user, and we add it to the history. So the next time the user speaks, etc., the assistant can still know like where it was in the conversation. But we need to find a way to tweak its sensitivity, let's say. That's something we will work on.
Okay. Does anyone have any other questions? If not, let's thank Enzo for this amazing talk.